Okay, hello everyone. In this talk I'm going to present to you the work that we did on distributed memory programming for reconfigurable hardware. So in the last years, the end of the NAND scaling and the crisis of Moore's laws have caused a major disruption in the computing landscape. Indeed, today, performance and energy cost of computation are mainly dominated by data movements. So in this scenario, reconfigurable hardware could be a valuable option to overcome some of the limitations of von Neumann architecture. In particular, thanks to the fact that we are able to lay down the circuit according to the application layout, we can avoid some of the overhead that are typical of von Neumann machines. So FPGAs are probably the most commercially diffused implementation of this kind of concept. And today, modern high-performance FPGAs are really attractive for HPC workloads. Indeed, they are equipped with native floating-point unit, high-bandwidth memory, and high-performance network connections. Furthermore, the diffusion of high-level synthesis tools is easing programmer lives, essentially helping the diffusion of this kind of devices also in high-performance scenarios. When we want to move to distributed memory programming, clearly we need a programming model for scaling our application on multiple reconfigurable devices. The problem is that today, when FPGAs are deployed in a distributed setting, usually communication is handled by either going through the host machine or by streaming the data across fixed point-to-point connection. So in the former case, we will go through the PCI Express bus, and therefore we will have this kind of overhead. In the latter case, when we stream the data across fixed point-to-point connection, we are sacrificing some of the flexibility that maybe could be helpful for programmers. So in this paper, we propose streaming messages, which is a distributed memory programming model for FPGAs that unifies both hardware programming with HLS with message passing. We propose SMI, which is an interface, an HLS communication interface that captures this concept of streaming messages. And we implemented and released an open source implementation for this, which is available on GitHub and targets Intel FPGAs. So before entering into the details of the interface, let's discuss what are the possible options that we could use for distributed memory programming on a reconfigurable hardware. So the first solution could be to resort to classical message passing, in which we have ranks that use local buffer to communicate data. Now suppose that we are in a similar scenario in which we have 4 different FPGAs that are interconnected in a ring, and we want to send something from FPGA 0 to FPGA 2. Now in HLS, programming FPGAs revolves around designing deeply pipelined circuits, and this is done by expressing the computation by means of loops that are pipelined in such a way that a different loop iteration could start on each clock cycle. Therefore, in this case, what we will have to do is that in our pipeline loop, we compute and we accumulate the data that we want to send in a local buffer here, and only when the computation is completed, we can send the data across the network toward the destination. Now, this is a well-known paradigm, and it is really flexible from the user perspective because endpoints can be specified dynamically, for example. However, this is a bad match for HLS programming because this relies on bulk transfer, while we would like to have a model that allows us to communicate while we compute. Furthermore, this requires potentially dynamically sized buffers that are difficult to manage in FPGAs. So another possible option that is currently employed is to stream the data across inter-FPGA connection using a point-to-point connection. So we are in a similar scenario as the previous one, we want to send something from FPGA 0 to FPGA 2. Now in this case, while we compute, we can push the data to the network toward the destination. Now in this case, the data must first go to FPGA 1, which proper logic will take it and route toward the final destination. Now this kind of model fits well with the HLS programming model, since we are communicating while we compute in a pipeline fashion. However, this is inflexible from the user perspective because the user has to construct the exact data path between the different points. For endpoints must be known at compile time, and the user has to handle all the forwarding logic. So in this case, for example, the data that goes to FPGA 1 is then routed to FPGA 2. And the disadvantage is also that if we change the network topology, we will need to essentially rebuild the bitstream. With our proposal, the streaming messages, we want to replace traditional buffered messages with transient channels. Yet the term transient means that these channels are open and closed dynamically. So here what we have to do is that we will open a channel here with this primitives channel, indicating that we want to communicate something to FPGA 2, something that has a given size. And then again, like the previous case, while we compute the data, we can push the data in the network. Now this combines the best of both worlds, because from one side we have that channels are transient established. We can specify ranks dynamically, for example, and we have a pipelined communication model, and we can communicate while we compute. What are the key facts of this approach? So we have that each of these channels is identified by a port, which is used to essentially lay down the proper hardware in order to allow the application to send the data or receive the data from the network. All channels, if we have multiple channels, they can operate in parallel, and we can program ranks in both single program or multiple program, multiple data fashion, with the advantage in the former case that we will need just one bit stream to reprogram all the devices in the clusters. Now, we designed an interface, streaming message interface, to capture this concept of streaming messages. In the interface, we have primitives for HLS programs, primitives that offer both point-to-point and collective channels. So for point-to-point channels, they are essentially FIFO queue that are used to send data from a sender to a receiver. So let me show in detail how the primitives look like. So suppose that we want to send something from rank 0 to rank 1. First of all, we have to open the channel here by using the open send channel primitives, in which we indicate the length of the message and the type of the message, integer in this case, the rank of the destination, the port number, and the communicator. Then later on in our pipelined computation loop, we will push the data while we compute. On the receiving side, symmetric operations are applied. So we will open a receive channel, again indicating the length of the message, the type of the message, and so on. And in the computational loop, we'll pop the data from the network. As I said, we can have multiple channels that operate in parallel. So in this example, we have two different channels of different types that are used to send data to rank 1 and to rank 2. And again, in the computational loop, we can push the data to both the channels. Now, in order to be meaningful, these kind of primitives must be implemented in such a way that data elements are sent in the order in order to preserve the correctness of the communication, and that these calls can be pipelined in a single clock cycle in order that they don't interfere with the rest of the computation. And this way, the communication is programmed in the exactly same way in which the data is streamed across intra-FPGA modules, which means different components that are instantiated on the same chip. For collective operation, we have collective channels that can be used to implement broadcast, reduce, scatter. So just to show an example, this is a broadcast example. Similar to the point-to-point case, here we specify the opening of a broadcast channel by indicating the length of the message, and in this case also the root rank. And in the computational loop we will broadcast the data. Now at runtime, the behavior of this broadcast clearly depends on the rank. If the caller is the root ranks, then it will push the data to the network, otherwise it will receive the data from the network. Like in the case of point-to-point communication, SMI allows multiple collective communication to operate in parallel. We discussed also about buffering and communication mode. So each of the channel in SMI is characterized by an asynchronicity degree k, which is a number greater or equal than 0, which means that essentially the sender can run ahead of the receiver of up to k data elements. Now the way in which this buffer is implemented actually depends on the implementation used. It can be essentially implemented with any form of on-chip memory, such as registers of VRAM. For the communication mode, in point-to-point communication, we can use eager communication modes if we know that the length of the message is less or equal than the asynchronicity degree k. Otherwise, we have to resort to rendezvous in order to ensure proper flow control. In the case of collectives, we cannot rely on flow control alone in order to ensure correctness of the communication. So consider the following example, in which we have data, we have the root rank, which is the rank 0, and all the different ranks that send their contribution to the root. So what could happen here is that rank I plus 1 could send its own contribution before rank I. Now we should remind that here communication are streamed. So in the root rank, we don't have enough buffer space to accommodate out of order data for any arbitrary number of ranks or any arbitrary data message size. Therefore, we need a way to ensure the correctness of the communication by synchronizing all the ranks that are involved. This depends on the used collective. So for example, in the case of the gator, what we need is that the root communicates at each rank when the root is ready to receive its own contribution. So we realized a reference implementation for SMI that targets inter-FPGA. So it's entirely written in OpenCL and it's available open source on our GitHub repository. So the implementation resides between the application and the network ports, and it's composed by two main parts. So the first one is the interface that implements primitives such as push, pop, broadcast, and so on, and is in charge of splitting the data in network packets and handling the flow control. Then we have a transport component which is in charge of routing the data across endpoints. So the port number that are used in the open channels primitives are used to lay down the circuit that is needed to move the data from the application to the network port and vice versa. So in our implementation, messages are packaged in network packets and are forwarded using packet switching. In our case, the network packet size is equal to 32 bytes, which is the width of the I/O interface that was available in our target architecture. So these 32 bytes are organized in 28 bytes of payloads plus 4 bytes of either information such as the source destination rank, the port number, the type of operation, and so on. Regarding the transport component, we have that each network connection is managed by a different pair of communication kernels in order to not have a single centralization point. These communication kernels are organized in the following way. We have a sender and a receiving communication kernel. They are connected to the application, and they are also interconnected between each other in order to forward the data properly. This communication kernel use a routing table in order to forward the data according to the destination rank. And this routing table is dynamically loaded, which means that if we change the network topology, we just need to rebuild the routing table and not the entire bit stream, which is clearly a great advantage and will save us a lot of compute time that otherwise would have been spent in synthesizing different versions of the bit stream. For what concerns collectives, they are implemented in support kernels. So since both sending and receiving behavior must be instantiated on each rank, they will be responsible for sending and receiving the data to the network, and they are responsible for managing the synchronization that is required for ensuring the correctness of the communication. In this reference implementation that we open sourced, we also define a development workflow. So we start from the source code that is provided by the user that essentially implements the business logic. And the user in this case can just use the SMI primitives, so open channels, pushing, popping, collectives, and so on. From this source code, we have a code generator that extracts all the information that are needed to build the SMI infrastructure. So the output of this code generator will be a device source code that contains all the SMI components, communication kernels, collective support kernels, and so on, that are needed in the application. And the code generator also outputs a no-stiller file that contains utility function that can be used at runtime. Then the generated device code and the user code can be compiled together in order to produce the bit stream. Again, just wanted to let you notice that for single program multiple data application, we just need one bit stream for the entire cluster. Then at runtime, we need a root generator that takes an input the topology, the network topology, which is expressed by a JSON file, in order to compute the routes for forwarding the data in the application. And at runtime, the host program, the user host program, can take advantage of the host generated function in order to load these routing tables and execute the application on a cluster. So the user will need just to use distributed launcher such as MPI run in order to let its own application run on the cluster. So in terms of evaluation, we evaluated this implementation on a cluster of 8 static 10. Each of these static 10 has 40 gigabit per second network connection. They are attached to the host by using a PCI Express bus. So this infrastructure is hosted by the Paderborn Computing Center in Germany, and the FPGAs are organized in 4 different nodes, which are in turn connected by using Omnipath at 100 gigabit per second. So the FPGAs are interconnected by using a 2D torus, and therefore we performed the evaluation considering 2 different kinds of topologies. Again, we just changed the topology file and we reused the same bit stream. So we used the 2D torus, which is the physical interconnection network, and also we considered a bus topology in order to evaluate certain performance metrics. So we evaluated the implementation of a different micro benchmark. Here in these figures, I'm showing you the bandwidth which is achieved in terms of gigabit per second, considering different message sizes. So for SMI, we evaluated the bandwidth considering different network distances between the source and destination rank, so 1, 4, and 7 hops. So in all the cases, the bandwidth is very similar as one would have expected, and we are able to approach the peak bandwidth of the network connection, which is 40 gigabit per second. Now we should notice that this gap between the achieved bandwidth and the peak bandwidth is also due to the fact that in our network packets we have also header information which are used for routing purposes, so not just the payload. In orange, we reported the host-based implementation of the same benchmark. So the implementation in which we copy the data to the FPGA DRAM, then we copy the data in the host, and we use the host interconnection network to let the data travel to the destination. Now, as you can see here, we achieve much lower bandwidth, and this is probably due to a poor implementation of the PCI Express interface in the BSP that we used. In terms of latency, we measured the latency in a microsecond, again by varying the the hop distance between source and destination rank. So for the host-based implementation, we are able to achieve around 36 microseconds, while the latency of SMI is usually one order of magnitude smaller, and clearly in this case the latency increases as long as we increase the network distance. In terms of resource utilization, for implementing the required SMI infrastructure, we are usually below the 2% of the resource usage of the entire chip. For the collectives, we evaluated broadcast. Now again, in this case, we have the time with respect to the broadcast size. So in this case, the lower the better. And in orange, it's reported the host-based implementation, and the other lines are the SMI implementation for both bus and torus topology. Clearly, the torus topology is able to achieve a lower completion time with respect to the bus topology, but in all the cases, we are able to beat the host-based implementation. For reduce, this is a similar benchmark to the previous one. In this case, SMI is able to perform better than the host-based implementation for small to medium-sized messages, while the host-based implementation performs better for large-sized messages. We should notice that in this case, this is also due to the fact that in the current implementation, collectives are implemented by using a linear schema. Therefore, this gap can be reduced and probably eliminated by using, for example, tree-reduced schema for implementing reduce. Also, in this case, we measured the resource utilization for the collective support collective kernel, and in this case, we are below the 1% of resource utilization. So we evaluated the SMI also on a couple of applications. So the first one is a multiple program, multiple data application, which implements JSON-V, which is a polybench kernel. So on the left side, it's reported the single chip implementation, which we have the 2 JSON-V that competes for the DRAM bandwidth, and then we have the vector addition to produce the final result. On the right hand side, we have the distributed implementation. We simply moved one of the JSON-V outside of the chip to the other chip. Now in this case, the 2 JSON-V can benefit of the entire bandwidth which is coming from the DRAM. And moving from the single chip to the distributed chip implementation just requires changes of a few lines. Now, in this graphs are reported that they achieved the speed up of the distributed application with respect to the single chip implementation for different size and shapes of the matrix. And in all the case, we are able to achieve the expected speed up of 2. We implemented also a single program multiple data application, which is partially tied to the Jacobi stencil. So the implementation is the classical one, in which the matrix is partitioned across the different devices and neighbors exchange Helio region on each time iteration. Now, being a single program multiple data application, we use the same bitstream to reprogram all the ranks. Now, on the left side is reported the speed up over one FPGA. So in the case of 8 FPGA, we are able to achieve almost 7 speed up, which is a good result. And on the right hand side is reported the weak scaling, considering 4 and 8 ranks. And as long as we increase the grid size, we achieve a scaling equal to 2. So in conclusion, in this work we presented the streaming messages, which are a programming model for reconfigurable hardware that unifies both traditional message passing with HLS programming model. We defined a streaming message interface which captured this concept by providing to the user a set of primitives for point-to-point and collective communications. We released a reference implementation that targets inter-FPGA, and we also evaluated this across different micro benchmarks and different applications in order to evaluate its effectiveness. So SMI is publicly available, and you can find it on our GitHub repository.